Okay. Okay. Good morning. I'm Marco Veranda. I work at Consortio Effects in Padova. And today I want to talk to you about Lagrangian Coherent Structures that are a method, a technique that helps us understanding better the topic of stochastic transport. And before beginning, I just want to give a quick definition of Lagrangian coherent structure that I will deepen during the talk. They are structures that represent a robust hidden skeleton that is able to organize the dynamics of turbulent and stochastic dynamical systems. So this is a study that was born in the framework of dynamical systems, in particular hydrodynamics at the beginning. And they seem to impact the transport of physical quantities at various levels. In the case of magnetically confined fusion plasmas, the Lagrangian coherent structure they reveal the structures that rule the transport of, for example, magnetic field lines, but also of particles, fast particles, and probably also at the microturbulence related transport. And we started using the Lagrangian coherent structure after discussion with Professor Francesco Pegoraro and Daniela Grasso, University of Pisa and Torino in Italy, because we had a fundamental question about the experimental activity in the device for magnetically confining fusion plasmas that we operate in Padova. It is a device that works in the reverse field pinch configuration that I will explain a bit for those who don't know it. And the problem or the question was that we observed strong electron temperature transport barriers in regions where the magnetic field is stochastic. And so we wanted to know what was sustaining these gradients in regions where you may think that there shouldn't be any gradient. So just a few words about the reverse field pinch. It is a configuration that is similar to the tokamak that was just described by Robin, but with the same toroidal magnetic field, we drive a current that is 10 times stronger. And this choice has consequences. A positive one, like the fact that the current can hit the plasma and up to high temperature and produce most of the confining magnetic field. And other consequences are, for example, that the toroidal component of the magnetic field spontaneously reverses its sign at the edge. And so you get a safety factor that has this shape very different from a tokamak. For starter, it is below 1 everywhere. And one can see that there are many rational values in this safety factor. So this means a lot of magnetic instabilities. They're interacting with each other, and this is a clear road to magnetic field stochasticity. But in the past, experiments and simulation showed that the reverse field pinch, when you increase the plasma current, spontaneously sets on a helical shape. And this helps about avoiding disruptions and also creating the electron transport barriers that you can see here in the picture. When increasing the current from 0.7 megaamp to 1.3, we get this huge increase in temperature and the formation of the internal transport barriers. Very interestingly, it is also possible to control the shape or the helical pitch of the plasma column by using proper small edge magnetic perturbation. And this is important because in that way we can control the level of chaos of the configuration. I want to show you more about this temperature gradient. And to do that, I introduce something that I guess most of you know, but and I introduce the Poincaré plot. Let's the Poincaré plot imagine to have a set of 3D magnetic field line in the torus. You look at them on a surface, on a selected surface. So you reduce the dimension of the problem of one, and you can have a visualization of the topology of the magnetic field. Here I choose a surface at a selected toroidal angle, And you see that at low current, the magnetic topology of the reversible pinch can be like this. So a magnetic field line that starts at a certain point that has a certain color can wander in the whole region of the torus. When we increase the plasma current, the situation changes. The plasma sets on a helical shape or on a quasi-helical shape. And you see that in the core, a region of conserved magnetic surfaces starts to appear. It's interesting to notice that there is always a chain of m equals 0 magnetic island at the edge. That is where the safety factor reverses, and they are the ultimate confinement for the system. But the most interesting observation is that the temperature increases a lot, and we get the formation of these electron temperature gradients. And if we, this is from a Thomson scattering diagnostic, and if we try to look for the region where there are these temperature gradients, we get into a region where the magnetic field seems to be stochastic. So there must be something else at play. And here we come to the topic of Lagrangian coherent structure and of turbulence transport.
The left-hand side, actually, yes, the first one seems to be related to
it's a little bit out of the, even in that case, it's a little bit out of the conserved region, because the conserved region may account for this plateau inside, but the temperature gradient is a bit, even on the let's say high field side, it's related, it's in a region where the magnetic field is stochastic. So yeah, but for sure here the role of conserved magnetic surfaces is more clear. We are closer to it. So yeah, that can be a case. I'll give you an intuitive explanation of the Lagrangian coherent structure and a sketch of the algorithm in the next part of the talk, and then some examples. I want to start from a step before, because on the past century, the study of stochastic transport in the framework of dynamical system, well, it started from the basics work of Henri Poincaré, and already him pointed out the fundamental role of the stable and unstable manifolds, in particular of hyperbolic dynamical systems, in ruling in mediating the transport of initial condition, the transport in the phase space. And here we have all the words like the clinic tangle, the Kolmogorov, Wagner-Moser toroid, counter-toroid, the fundamental role of loop dynamics. But this topic is quite difficult, at least from my point of view, from the mathematical point of view. And so in the last 20 years, there was like a necessity of having a simplified vision of this kind of dynamics. There were many ideas that were put forward, for example, connection length, streamers, Poincaré return time. Today, I want to discuss Lagrangian coherent structure and finite time gathering of exponents. Lagrangian coherent structures, an hyperbolic Lagrangian coherent structure over a finite time interval, this is important, over a finite time interval, is a locally strongest repelling or attractive material surface over that time interval. The fundamental work is one by George Haller, who works in Zurich from the year 2000. And we can see in a simple example, imagine you have already computed an attracting or a repelling Lagrangian coherent structure. You get a parcel of fluid at the beginning, you evolve it in time, and you see that the effect of an attracting Lagrangian coherent structure is that of attracting the fluid or repelling it. In the next few slides, I want to show you how you can compute these structures. First of all, well, this may seem silly, but one has to choose the dynamical system of interest. And I say this because the technique is very general. It can be applied to velocity in hydrodynamics. I've seen it applied to, for example, the electrostatic potential in gyrokinetics, or as I will do, to magnetic field lines in MHD. And then you have to choose a set of properly gridded initial conditions. Here, just for the sake of explaining, I chose a set of 25 squares, each one with consisting of 5 initial conditions. In realistic cases, you need much more. What do? You evolve, let's take, for example, a square. You evolve it under the flow map of your dynamical system for a finite time. And what will happen is that the square will get transformed into this shape. Given this transformation, you can always compute the so-called Cauchy-Green strain tensor that is related to the deformation matrix of the flow map. And from this matrix, we are in 2 dimensions here, so you can get 2 eigenvectors, one in pink that is associated to the maximum contraction of the square, and the one in green that is associated to the maximum stretching. Of course, associated to the eigenvectors, there are 2 eigenvalues, and you can define the finite time Lyapunov exponent field in this way. It is related to the absolute value of maximum stretching. The point now is that you do this evolution for all the set of initial conditions, you get to a situation like this. This is purely pictorial, I want to stress. And then you have to compute a repelling Lagrangian coherent structure. Well, the definition is that a repelling Lagrangian coherent structure is a curve, gamma, that is everywhere tangent to the minimum eigenvector. And being this a differential equation, you have to choose an initial condition to integrate it. It's wise to start from local maxima of the deformation, for example, this point. And you can easily see that by integrating this equation, you get a line that follows a curve that follows the minimum eigenvector, the yellow one. And it is clear that along this line, the repulsion of initial condition is maximized because orthogonally to it, you got your direction of maximum stretching of the system. And of course, you can also associate to each Lagrangian coherent structure a rate of repulsion. And it is clear that you can compute a Lagrangian coherent structure from every point. Only few of them will have a maximum repulsion. Only few of them will be interesting ones. And here I have a set of more rigorous definition for a Lagrangian coherent structure. This is the equation that I just discussed. The first condition tells you that the Lagrangian coherent structure is everywhere orthogonal to the gradient of the finite time Lyapunov exponent field, meaning that the gradient of the finite time of the FTLA field is orthogonal to it. And anyway, in any case, all these equations are discussed in big detail into this work by Giovanni Di Giannatale, who will be here next week. So you can also discuss with him this topic. This technique is an interesting one, I'll show you later, but it has some, I wouldn't say problem, but some things that need to be discussed a bit more carefully. First of all, the role of the finite time is fundamental, and it is very system dependent. So one has to try a lot to understand what is the correct finite time to observe the stochasticity of magnetic field line or of the dynamical system. The second is that you need to integrate quite a lot of initial conditions, and this is no more a problem, I guess, because it is feasible in modern high-performance computer. Still, the results of the method involve some subjectivity on the side of the human being that is looking at the resulting Lagrangian coherent structures. In the sense that it seems to me that it is difficult to automatize. You have really to look case by case the result that you get. So after this definition, I want to show you one example from reverse field pinch. I choose the dynamical system given by the magnetic field lines. And to do so, I need a magnetic field, okay? And I get this from a numerical simulation of the reverse field pinch. I just want to say a few words about the model that we use. It's a three-dimensional, nonlinear, viscoresistive MHD model whose equation you have here. There is the momentum equation, the induction equation, and it is solved in cylindrical geometry with the approximation that are good to describe the physics of the reverse field pinch that is mostly current driven because plasma current is relatively high on a reverse field pinch. And an interesting feature of the model that I just wanted to say is that its dynamics is ruled by one parameter in the end that is related to resistivity and viscosity of the plasma, and this parameter is a good order parameter for the possible dynamics of the system. In the next slide, I show you these two Poincaré plots. These are from simulations of the reverse field pinch. You got a non-helical state on non-helical state on the left and a quasi-helical state on the right. I haven't here a picture of the dynamics of this quasi-helical state, but they reminded me of the, how did you call them? The failed laminarization event. It seems something like that because the system tries to go to a laminar flow with very well conserved magnetic surfaces, but it fails at the values of the resistivity and viscosity that we are. But this may be a failed laminarization state. And in any case, you see that there is a wide level of stochasticity that I want to analyze using Lagrangian Coherent Structures. Before doing that, I want to show you another tool to understand more. Here I plot the connection length. The connection length is the parallel length that a magnetic field line starting at a certain point has to run to arrive, in this case, to 0.75 in the radial position. Connection length is interesting because it already tells you that below stochasticity there is something. For example, in this case, you can see that there are regions where there are sudden drops of the connection length that are not revealed by Poincaré plots. I take another step and I compute for the multiple helicity case, for the non-helical case, I compute the finite time Lyapunov exponent in this picture. Here you can see something more because you can see that hidden in the stochasticity, there are actually some very interesting structures that are the regions where the finite time Lyapunov exponent reaches the field reaches the highest level. And these are very interesting because you can see here, for example, these lobes, this structure that are reminiscent of the homoclinic tangle. For those of you who know the homoclinic tangle is what happens when you slightly perturb a pendulum, for example, you get that particular picture that was imagined for the first time by Henri Poincaré, and it seems to be the same feature in the region where the magnetic field is stochastic. I show you the same picture for the QSH state. And one notices two things. Well, first of all, that the absolute value of the finite time Lyapunov exponent field decreases a lot. This means that the process of setting in a helical shape starts a process of healing of the magnetic gauss. But also you can see that there are clear structures here in the finite time Lyapunov exponent that can be revealed by calculating the Lagrangian Coherent structure. In the next picture, the black lines are the Lagrangian Coherent structure for the two cases that we just saw. The contour plot in this case is a computation of the temperature made by a code, and that assumes that the heating is only of ohmic kind. I want to do some consideration about this picture. First of all, Lagrangian coherent structures like here or here, they separate quite well regions where the plasma temperature, the electron temperature, has some gradients. Okay, so they seem to be a good candidate at this point for understanding why there can be gradients also of temperature, also in stochastic magnetic field. The second consideration, yes?
Quick question.
Yeah.
These things look rather thin. How many gyro radii across are they?
They can be, they are, it depends, okay, but for example, these tight ones, okay,
The black one
the
there,
black
you
one, they are few some electron gyro radius, but they are ion, they are let's say half, they are minor than the ion gyro radius. They are of the order of the ion gyro radius. Yeah, that's important. Yeah. The barrier in
gyro radius has an impact on instabilities that can affect electrons.
Yes. Yeah. One has to keep into account also the possible micro instabilities that sets in the electron temperature gradient.
Micro instabilities that get you through the barrier. Exactly.
But here the consideration that I want to make is related to the shape of Lagrangian coherent structure. In this case, they are tightly packed in let's say generalized radial direction that you can find by a suitable coordinate system to keep into account the helical shape of the plasmas. And here we observe a strong electron temperature gradient. While in the non-helical case, the Lagrangian coherent structures can span a long radial direction. And by looking at their shape, by looking at the structure that are surviving in the stochastic region, probably the separatrix, what remains of the separatrix of magnetic island after they interacted with each other, the bunch of heteroclinic tangles that seems to be active in this region, they can tell, their shape can tell you how magnetic field lines are transported across a stochastic magnetic field. This situation is very similar in magnetic field like taken from the experiments. I have some picture that I didn't have time to put in the presentation, but the point, sorry, yeah.
Just to be sure.
Yeah.
The color corresponds to the temperature, the electron temperature,
The electron
and the black lines to the
Lagrangian coherent structures. Yes. And well, the temperature is computed by a Lagrangian code that computes the temperature solving the transport equation and assuming that the only heating is of ohmic origin. That is a quite good assumption for the reversible pitch.
And how does it compare to the
Well, the temperature or the that's we are not yet quantitative on that aspect. We observe profiles that are compatible with the experimental region, but at the moment we are not able with our simulation to reach the Lundquist number that is present in the experiments, and also the anisotropy in the diffusion coefficient, on the heat diffusion coefficient. That is up to a level of 10 to the 10 to the 11. This simulation was made with 10 to the 6, 10 to the 7, maybe, to get like a good comparison between the temperature that we observe and the results of the simulation. We need to increase both a bit, both the Lundquist number and both the anisotropy. So, but the path seems to be the correct one because we observe the temperature gradients that are very similar to the experiment.
That mentioned
Mhm.
some gradient, nitrogen moves.
Yes. Yeah, there are some in the region of the gradients there seem to be micro instabilities of microbearing mode. They contribute to stochasticity, both of them. What doesn't seem to be present are ion temperature gradient modes. Those were seen to be at the limit of stability in that situation. But yes, this topic is important because for now we discovered this, we computed this Lagrangian Coherent structure for magnetic field lines. Of course, this is true at the 0th order because we know that particles are not following magnetic field lines in the strictest way. There is some zero radius. And the next step that we want to do is to try to use this technique to follow the dynamics of particles and see whether thermal particles or a suprathermal particle has its own set of Lagrangian coherent structure, how different they are from the one that you can predict by simply looking at magnetic field lines. That is a step that wasn't taken already.
Macroscopically, how would you operate to make these things, to exploit it?
Well, one thing that we can do, for example, is we have seen that by using proper edge magnetic perturbation, we can change, for example, the helical pitch of the magnetic island. That has an influence on the quantity of conserved magnetic surfaces and of chaos. I may have a picture in my spare slides that sorry, so many slides. Wait. Well, the picture has disappeared, so I will have to tell you this by word, okay? We can, for example, the case that I showed you as a helical state that wins around the torus 7 times. We showed that if you use a perturbation at the edge that has a 6-time periodicity, that kind of changes the nature of the helix, you get wider regions of conserved magnetic surfaces and a lower level of chaos. So by trying to negotiate with the plasma, the better or the best helical state, we can change the chaos. And then, of course, there will be the difficult way of increasing the temperature, but the plasma current. But that would require another bigger experiment, so that is more, at least it's more expensive. So I come to a final remark about Lagrangian coherent structure. They can help understanding.
Move back
to the full screen. Yeah. Let me see. Control L. Yeah. They can help understanding the features of nonlinear transport in many situations. It's important that here I showed only the case of magnetic field lines, but they can be applied to a wide set of modeling and of experimental data. For example, they are interesting to understand the mechanism at the basis of formation of internal transport barriers. I guess that up to now, we are still looking into the experimental data from the RFX mod device, but they are at present the best candidate to explain why we observe temperature gradients where there is stochasticity. And this can be applied in other devices and in other modeling frameworks. And in particular, it can be interesting, and we will probably do it in the future, to do that, to study the magnetic topology in other scenarios from tokamak MHD. It is interesting, for example, the case of plasma that are penetrated by edge magnetic perturbation, because there you can get local stochasticity, or maybe during disruption or during the sawtoothing dynamics in the core of the token. With a step forward in the mathematics of the Lagrangian coherent structure with, I think, the correct dynamical system, one can study also the role of the transport of particles and possibly of fast particles and runaway electrons. And so the Lagrangian coherent structure can help seeing better what happens to those physical quantities. I guess this is all. I have here a minimum, really minimum bibliography starting from Haller 2000. And then in the last 20 years, this technique is spreading from hydrodynamics to fusion plasmas, for example. And that's it, I would say. So I wait for your questions.
Is there any connection between Lagrangian coherent structures, let's say, invariants of one thing that I've seen, there's some cases like fluoride, which is the high. It's still
Yeah. That's exactly what the point is about Lagrangian coherent structure. They reveal structure that are very well known in dynamical system, in perturbed dynamical system, and we really believe that the one that I showed you correspond to broken KAM tori that are called cantori, and so those are leaky, let's say, conserved magnetic surfaces. This is not well said because they are not conserved, but they are almost conserved, the cantori. So they have small leaks through which the magnetic field line can go out. And so we can do we can make the connection between LCS and cantori, even though revealing the cantori by directly looking at them in the Poincare plot is an extremely difficult work. Okay, so we rely on the easy way, that is the Lagrangian coherent structure. But it is interesting if once I try to put the initial condition for the magnetic field line with the excruciating precision, and you can see the cantori, you can see the tangle, okay, even in the chaotic field. But it is very difficult, and it is certainly not feasible when you have well-developed chaos. I did it in a simplified case, impossible, and so that's why we do Lagrangian coherent structure that seem to be cantori in some cases. There was maybe.
Yeah, the Lagrangian coherent structure seems to be very.
Yeah.
Did you emphasize another
Yes. In those cases, to get data that are acceptable, you need to go to the tens of millions of initial conditions, and so that requires a supercomputer. Because otherwise, you cannot integrate the minimum eigenvector with the sufficient precision. There are always maybe small numerical error inconsistencies that makes that integration quite difficult. I didn't mention the details of that integration because they're written in the paper by Giovanni Di Giannatale. But you need to go to a very tiny resolution to have a smooth computation.
How did you decide to design?
By trying from
Trial and error.
from trial and error. Yeah, that's a negative part of the technique, because every time I analyze something different, I have first of all to understand the correct finite time. If you take it too long, you lose the exponential separation of magnetic field line in a stochastic field. If you take it too little, you don't give the chaos the time that, let's say, to breathe a bit, okay, and to be revealed and so on.
So how long does this coherent structure last in a real life?
one can say that they last just for the finite time that over which they are computed. And this,
What's the time scale? I mean,
yeah, the time scale is it is longer than a collisional time in the typical RFX case. It is a bit longer than so they survive for sure a bit longer than the collisional time.
So what is it, I mean, these things come to the fore in the QSH state.
Yes.
What is it about the QSH that we make is conducive to their, shall we say, formation or otherwise effectiveness? Again, it gets back to the question, what is the route to formation?
I think in this case, we are still speaking about macro instabilities, about interaction of macro instabilities. So the, let's say, heteroclinic tangle of the dominant mode and the secondary one that are still working, they are not completely annihilated by the failed laminarization process, but they are strongly reduced. So I guess there is now there is the possibility for the residual KAM tori, the cantori, to survive and to be at least less leaky, even less leaky. And so the Lagrangian coherent structures simply look at those structures. They see them in a more clearly way.
In some sense, it's because the QSH brings a kind of turbulence control, which gets you to kind of this weakly or marginally turbulent state where these things emerge.
I guess it's a weakly macro turbulent state, and we are at the more or less at the level in the best QSH state. I did a work a few years ago with some colleagues of mine, and the diffusion coefficient, when you consider micro tearing in the very best QSH state that we have, is comparable to the one of coming from the top from macro instabilities. So we are in the region, in the terrible median region where there is both macro and micro instabilities. We should try to go down, but the question would be there in any case, because even micro tearing can create regions of localized stochasticity. And so
is it possible to try to do a pulse propagation study in these things? In other words, you have, a game with modulated ECH, you put, I don't know if this works in an RFP, but it's a standard game in token physics. I mean, you stick the resonance near the region of interest and you look at the response to the perturbation.
Yeah, I mean, we are in the process of rejuvenating our experiment. In 1 year, it will be ready. But I don't think we will have the possibility of ECRH or of trying to do those studies of conduction of it that are possible in the machine, because that would be a very good experiment to validate this idea. I can try to do maybe something in the simulations, because, for example, if I go back to this picture, if I place a set of initial conditions here and a set of initial conditions on the other side of the Lagrangian coherent structure, I see that they remain separated. I wonder what would happen to a set of initial conditions of heat. Okay, I don't know. So we will see, I hope. But maybe we find a way of doing that experiment in the next few years.
I guess because it is quite small, in order to better understand the precisely how, where are these things have you tried to calculate those several parameter steps in the establishment of correlate with not using them or the magnetic field, but for instance, of the field itself, or
not on the magnetic field, but
on the flow pattern, the velocity, or the electric potential, in order to see these things.
Yeah, that's a good idea. I did like a scan in the time of during the evolution of the magnetic field from non-helical to helical state. And you can see that the Lagrangian Coherent structure have an evolution because these two cases are in during the same simulation before and after the establishment of the helical state. So they evolved during that time scale. But I didn't do the Lagrangian Coherent structure of the flow field, of the plasma velocity field. That was an idea, and I think I will try to do that because for sure the interaction between magnetic structures and flow is an important topic. So I didn't do it, but I will. The potential, the electrostatic potential, I should think about it. But it's feasible because for sure I want to quote this paper by Catherine Padbeck, I guess, of 2007. And she took the fluctuating electrostatic potential. I don't remember if from gene simulation or if it was just more an exercise with some potentials. And she computed the first step of Lagrangian coherent structure. So it is feasible and already done.
I have a follow-up remark related to the issue of Cantora. So it is right. Clear that chaos and the two lines, the two mathematical objects have Cantora. But the problem is that computing them is formidable. And if you compute one, this is a lot of work. And finding the best one, the one which is really confined, is really tremendous. And so what is fantastic with Lagrangian coherent structure is that you have a tool which gives you very rapidly, with respect to the band case, very interesting information. So it is not a perfect tool, but the other one is not amenable to complete realization as yet. Development of computers and mathematics possibly to come. But okay. So this was my first problem.
I want to just I interrupt you for a moment because I have a picture about this. Okay, for this much simpler stochasticity. Here, after trying for weeks, okay, in my free time, let's say, I was able to put the initial condition in a way that you can see the homoclinic tangle of this magnetic island of this, I was saying pendulum, okay, and you can see it here that it makes the clear lobes that you imagine there to be, but it was painful. Nothing more to say, please.
So the second follow-up is an explanation why the presence of these cantori are so efficient to produce barrier. And the reason comes from the renormalization theory for Hamiltonian chaos, which shows that the best cantori can be characterized by a critical exponent related to the flux of orbits through the area which flows through the contours on the point and time. And this exponent of this flux is 3. This means that the flux through the contours is like the distance to the shape of parameter. You have a critical value, okay, and the difference between the actual value of the parameter and the critical value is the third power. But this means that the flux increases very, very slowly when you go above there. So it is clear you destroy the Gaussian tau. And with this exponent almost 3, the flux increases very slowly above pressure. So this is the reason why these objects are very good.
I wonder if one can compute that critical exponent through this technique, but I don't know. I should think about it.
Okay. In the list, you show that the examples, I mean, except maybe Tabler, just mentioned, in most cases, I think are 2 or 3 dimensionals, and of course, the alternatives require 4 dimensions. So I was wondering how it goes in terms of CPU resources, particularly the number of neutral connections.
Yeah. That is a good question. I don't know, because I'm thinking in these days about going from 2-dimensional to 3-dimensional to observe how Lagrangian coherent structure evolve in time. It changes just that you have 3 eigenvector of your deformation matrix, and okay, you can always find a bigger one as a minor one. 4-dimension, that still probably is one of those things that is still difficult to compute. My first guess would be if I do a rule of thumb, imagine you have 10 to the 6, you have 2 more dimensions. You go to, I don't know, 10 to the 12. I don't know, that's just like that. And 10 to the 12 is like a dimensional number for the core of the Earth. It's still something that you say, maybe not, okay, maybe I try something else, or I try some other technique. I should think about it. Or one has to find ways to reduce the dimensionality. Padberg works in 2 dimensions, and there it is, you can do something. But I'm not that expert on gyrokinetics to know whether a realistic problem or interesting problem can be reduced to 2 dimensions. That's I will have to ask you, I guess.
There are some cases, but
Yeah.
the development phase.
Yeah. But maybe with the next generation computers, we can reach that level, even though I'm not a fan of waiting for the computer to do our work.
Questions? So let's thank our speakers.